Okay, so a little experiment that I quite like, which is a kitchen science experiment, but also quite useful for explaining why we might like to do computational models of things and simulations. What we're going to do is we're going to make up a little bit of jelly, and we're going to diffuse some dye through it. So to make the jelly, and I just showed this, but I'm sure you know how to make jelly, but I just show this because otherwise the jelly is quite clear. You need about a teaspoon of gelatin, and that makes up with about 250 mils of hot water, so about yay much. And we'll give that a stir. And I'm just going to pour it into a clear Petri dish. White dish or just about anything would do. Something that will let you see the colour is the only thing. So if I pour that in, now normally we would have to let that set in a fridge somewhere for several hours, but we don't have several hours, so let me move that aside. And here is one that we made earlier. And so it's just a clear jelly in the Petri dish. And I'm going to take the straw and I'm just going to cut a little hole in the middle. And I'm just going to, whoops, I'm not very good at flicking the bit out, and I forgot my screwdriver. Sometimes I use a little flathead screwdriver to flick that bit of jelly out. And I'm going to drop into that little hole that I've just made a little bit of red food colouring. And then what we'd normally do is put that in the fridge for about 4 hours or overnight or something like this. And again, we haven't got that long, so we're going to switch to one that we made earlier. Now what's going to happen is the food colouring, it can't flow out into the jelly, but it can diffuse out into the jelly. So the jelly's set, so the liquid's not moving through it. But all the little random particles are moving randomly. And so to start with, at time equals 0, they haven't had a chance to get anywhere. But as time goes by, their random movements, well, they've got longer to get further out. But some of them are going out and some of them are coming back in. And so it's not going to be even. And so you kind of get this fringing effect as it diffuses and blurs through the jelly. Now, it's a lovely little kitchen experiment in terms of diffusion. But it's also got a couple of little limitations I like, which is kind of where the simulations come in handy. Because already, twice, I've had to do, here's one I made earlier, because we'd have to wait several hours for the jelly to set, then we'd have to wait several hours for the diffusion to happen. If we wanted to have a look at how diffusion varies with temperature, if we assume it's random movements, well, we can't really see it happening, and we've got a problem that it's a nice kitchen experiment, but we've only got a fridge at one temperature, and we've got a pretty narrow range of temperatures where the jelly's going to work. If we warm it up too much, it's going to melt and it'll just flow everywhere. If we cool it down too much, it's going to freeze. And so instead, what we're going to show is a little simulation that lets us explore that aspect of random movement of particles and how that can vary with temperature. Not quite the same as an experiment, but it lets us explore the effect if we're confident that that's the effect that's going on.
If I'm confident that the random movement of particles is what's creating diffusion, then one of the things I might want to do is take that theory and put it into a computer simulation or a model and play it forward to explore its ramifications. Now, this isn't the same as doing an experiment. In an experiment, we do something in the physical world and we give ourselves some confidence that a theory is what's happening in reality. In a simulation or a computer model, we take a theory that we're pretty confident is what's going on in the real world and we explore its ramifications. Okay, if this is the case, what would we expect to see happen? Now, as well as letting us do things a bit more quickly, so in the time I've been talking I've already run this twice, it also lets me abstract away some parts of physics and only look at the particular bit that I'm interested in. So what I've got in this simulation, I have about 1,000 light blue circles representing the jelly. I've got about 200 purple circles representing the dye. And as in the Petri dish, we start the dye molecules off in the middle. And because we're saying we think this is caused by the random movement of particles, at every tick, the simulation just moves those circles a certain amount in a random direction. And then I've got this circle here, which is a measuring circle, and at tick is 500, we chart how many of them made it outside the circle. Now, I ran that one with them not moving very far in each tick, and none of them really made it outside the circle. So this was down here. If I turn that up a bit more, I will start to see, well, let's go to 15. And so now they're moving a bit faster, and some of them will make it outside the circle, and at tick is 500. We will start to see, let's find out, about 133 made it outside the circle. If I turn that all the way up to, say, 25, well, we'll see that they're managing to diffuse outside the circle quite quickly, and so then there's some outside the circle that could move back in again. And so we start to see the curve that we're collecting from this flattening out. And so, it went up like this, and then it started to flatten out because things had diffused and were a bit more even already, and so the ones moving out of the circle were starting to get a bit balanced by the ones moving back into the circle. Now, in that, I have only looked at the particular bit of physics I want to look at, random movement of particles. I don't have jelly freezing, jelly melting, the size of the diet molecules, all of these other things going on. Whereas when I run this physically in the Petri dish, the whole of physics is going on inside that Petri dish. So this is kind of one of the differences between experiments and simulations. In an experiment, we do something in the real world and explore something to give us confidence as to whether that is what is really happening. In a simulation or a computer model, we can take some theory we're confident what's going on in the real world, and we can explore its ramifications in a simplified form, looking at just the phenomenon, the rules, the behaviors that we're interested in, playing them forward, saying, if that's the case, what would we expect to see? And we can do it a lot more quickly. I haven't had to wait for jellies to set. I haven't had to wait hours with them in fridges at different temperatures to do that.